Welcome to Quantlock. Today we're diving into something called the Quantum Approximate Optimization Algorithm, or QAOA for short. It's a really powerful tool from the world of quantum computing, and it's being designed to tackle problems that are pretty much impossible for even our best regular computers. So here's our game plan. We'll kick things off by looking at the sheer scale of the problems we're trying to solve. Then we'll introduce our quantum hero, QAOA. We'll get into how this actually works, do a quick reality check on its performance today, and wrap up by dreaming a little about where this could all take us. So let's get into it. To really get why QAOA is such a big deal, you first have to understand the size of the mountain that we're trying to climb. And it's not an exaggeration for effect. This isn't science fiction. It's a real daily challenge in fields like finance, drug discovery, and logistics. We're dealing with problems where the number of possible solutions just explodes. The official name for this headache is combinatorial optimization. So picture this, you have thousands of delivery trucks. What's the single best route for all of them to take? A classical computer's only real strategy is to check every single possibility one after the other. But the number of routes grows so unbelievably fast that it would literally just take longer than the age of the universe to check them all. It's not just that it's slow, it's physically impossible. And that's exactly why we need a totally new playbook. So if our trusty classical computers are hitting a brick wall, what's the alternative? Well, let's meet a quantum approach that's designed specifically for the kinds of quantum computers we can build today. Now, the most important word on this slide is approximate. QAOA isn't about spending forever to find that one specific perfect answer. The goal here is to be clever and efficient, and to find a good enough solution that it still is incredibly useful out in the real world. What makes QAOA so interesting is that it's a hybrid. Think of it as a team-up. It uses a classical computer to do the heavy lifting and the strategizing, and it uses a quantum computer for what it does best, exploring a mind-boggling number of possibilities all at once. This teamwork means that the quantum part of the job can be kept short, which is a huge advantage because today's quantum computers are still kind of noisy and prone to errors. So let's pop the hood and see how this partnership works. This conversation between the two types of computers actually works. It's a pretty slick process. You can think of it as a feedback loop. The quantum computer acts like an explorer. It uses superposition to check a huge number of paths at the same time. After each attempt, it measures the result and sends its best guess over to the classical computer. The classical computer then acts like a guide. It looks at the result and says, okay, this was pretty good, but try changing your settings just like this and go again. They repeat this little dance over and over. But before that loop can even begin, you have to do a bit of translation work. Your real world problem, let's say optimizing a stock portfolio, needs to be converted into a mathematical language that the quantum hardware can understand. That language is called QAOA, and it basically turns a complex problem into massive strings of yes or no questions. Now I know this equation looks a bit scary, but the idea is pretty just simple. This is our problem in that QAOA language, C of x. You can think of that as just the cost of any given answer. For our delivery trucks, a high cost would mean wasted time and fuel. The little x's are the whole possible choices, represented as either 0 or 1, a no or a yes. The entire goal of this whole process is just to find the combination of zeros and ones that make that final cost as low as possible. And now we translate it again, this time for the quantum chip. This is called the cost Hamiltonian. It's the exact same problem, just written in the language of quantum physics. See, quantum computers think in terms of energy states, so the lowest cost in our original problem now corresponds to the lowest energy state for the quantum computer to find. Same goal, just different language. So the quantum computer is juggling two big instructions. The first one is that cost Hamiltonian is at gravity. It's always pulling the system towards good, low-cost answers, but you could get stuck in a small valley. A pretty good answer, but not the best one. That's where the second instruction comes in, the mixer Hamiltonian. Its job is to give the system a kick, to jiggle it around and help it hop out of those small valleys so it can explore the whole landscape and find the deepest one, the true best solution. So the theory is beautiful, it's elegant, but this is where the rubber meets the road. How can all this theory actually hold up when we run it on the quantum machines we have right now? This table tells a really important story. Just look at the gap between the score and a perfect computer simulation versus a score on real hardware. In a flawless imaginary world, the algorithm does great. But when you run it on today's noisy, error-prone quantum devices, performance takes a pretty big hit. This is just a reality of where we are in the development of this technology. And the hardware noise isn't even the only problem. Just figuring out the right settings for those cost and mixer steps, those parameters from the loop, it's a really hard optimization problem on its own. And frankly, for a lot of problems today, our best classical algorithms are just plain faster. It's also worth pointing out that QAOA isn't the only quantum game in town for these problems. There's another approach called quantum annealing. They're trying to do the same thing, but they go about it very differently. Quantum annealing uses specialized purpose-built hardware that kind of smoothly relaxes into the right answer, which means you don't have to deal with all the tricky parameter tuning that makes QAOA so tough. But to get around these challenges, researchers are getting incredibly creative. This table just shows a few of the different flavors of QAOA that people are developing. Each one uses a slightly different trick or strategy to try to boost performance and be more efficient. It's a field that is moving and changing incredibly fast. Now, despite all those hurdles we just talked about, there's a reason for all this excitement. The potential payoff here is enormous. Let's connect this all back to the impossible problems we started with. I mean, the list of places this could be used is just transformational. We're talking about everything from designing a perfect investment portfolio, to making AI models train faster, from optimizing flight schedules for an airline, to securing our communication networks. A truly workable quantum optimization algorithm could touch pretty much every industry you could think of, and at the end of the day, as his quote says so clearly, the future of QAOA is completely tied to the future of quantum hardware itself. The algorithm is only as good as the machine it runs on, so they both have to improve hand in hand. And all of that leaves us with the big open question. As we look ahead, is QAOA the only thing that's finally going to unlock a true quantum advantage? Or is it going to be more of a brilliant but temporary stepping stone on a longer journey toward an even more powerful quantum algorithms that we haven't even invented yet? Right now the answer is still being written. Thanks for watching. This was Quantlock.